Welcome to Chapter 7 lesson, the transport layer. In this chapter, we will examine the role of the transport layer in encapsulating application data for use by the network layer. We will explain the need for the transport layer, also the role of this layer as it provides the end-to-end transfer of data between applications, as well as explaining the key functions of the transport layer such as reliability, port addressing, and segmentation. Let's begin by describing the role of the transport layer. It is responsible for establishing a temporary communication session between two applications and delivering data between them. As we can see in the figure, the transport layer is the link between the application layer and the lower layers that are responsible for network transmission. It provides a method of delivering data across the network in a way that ensures the data can be properly put back together on the receiving end. In the TCP/IP, desegmentation and reassembly processes can be achieved using two very different transport layer protocols: Transmission Control Protocol, or TCP, and User Datagram Protocol, or UDP. Primary responsibilities of transport layer protocols are tracking the individual communication between applications on the source and destination hosts, segmenting data for manageability, and reassembling segmented data into streams of application data at the destination, as well as identifying the proper application for each communication stream. We will now revise these responsibilities. Tracking individual conversations. Each particular set of data flowing between a source and a destination application is a conversation. The transport layer tracks each individual conversation flowing between a source and a destination application separately. Segmentation. The transport layer divides the data into segments that are easier to manage and transport. It allows conversation multiplexing, which means that multiple applications can send and receive data in the network at the same time. Identifying applications. The transport layer ensures that all applications receive the correct data by assigning each application an identifier or port number. Each software process that needs access is assigned a unique port number. The transport layer uses these ports to identify the correct application. The transport layer is responsible for managing the reliability requirements of a conversation. The protocols used are TCP and UDP. TCP is considered a reliable, full-featured transport layer protocol, which ensures that all of the data arrives at the destination. On the other hand, UDP is a very simple transport layer protocol that does not provide for any reliability. The downside of TCP, however, is that it can cause additional overhead and possible delays in transmission. In such cases, UDP is a better transport protocol. It provides just the basic functions for delivering data segments between the appropriate applications, with very little overhead and data checking. It is a best effort delivery protocol, as there is no acknowledgement that the data is received. It can be seen as sending an unregistered letter by mail, as the sender cannot be aware that a delivery was final. If we analyze TCP, we can realize that it includes processes to ensure reliable delivery between applications through the use of acknowledged delivery. It can be seen as a service that tracks packages from source to destination. As we can see in the video, it has three basic operations: tracking transmitted data segments, acknowledging received data, and retransmitting any acknowledged data. TCP breaks up a message into small pieces or segments. These are numbered in sequence and passed to the IP process for assembly into packets. TCP keeps track of the number of segments sent. If there is no response of the message being received, it is assumed that the message is lost and it resends it, but only the portion of the message that was lost, not the entire message. On the receiving host, TCP reassembles the message segments and passes them to the application. Examples of applications that use TCP to ensure the data was delivered are FTP and HTTP. Now the question arises of how do you choose between UDP and TCP? As we can see in the picture, depending on the application requirements, application developers must choose which transport protocol type is appropriate. Some applications need segments arriving in a very specific sequence to be processed successfully. Others may need to receive all the data in order to consider it useful. Usually for both instances, TCP is used. Examples of applications that use it are databases, web browsers, email clients. They need the message in its original condition without missing data or be corrupted. Network overhead is considered a requirement, though. When an application can tolerate some data loss during transmission, but delays in this transmission are unacceptable, you use UDP, as less network overhead is required. Some examples of applications that use UDP are streaming video, audio, voice over IP, or internet radio, as acknowledgements will slow down delivery and retransmissions are undesirable. We will now explain how each protocol implements specific reliability functions and how they track communications. Let's start with TCP, Transmission Control Protocol. It provides the basic functions of data segmentation and reassembly, but it also provides connection-oriented conversations by establishing sessions, reliable delivery, order data, reconstruction, flow control. Let's analyze them. As we can see in the picture, establishing a session. As a connection-oriented protocol, it negotiates and establishes a permanent session between source and destination devices prior to forwarding any traffic. Through this process, devices negotiate the amount of traffic that can be forwarded at any given time, so communication data can be easily managed. Now let's check reliable delivery. It ensures that each piece of data that the source sends arrives at the destination. It takes care of retransmission of lost or corrupted data. Same order delivery. By numbering and sequencing the segments, it can ensure that these segments are reassembled in the proper order. And flow control. When it notices that memory or bandwidth is overtaxed, it requests a reduction of data flow by regulating the amount of data the source transmits. This can prevent the loss of segments and avoid retransmission. We will now analyze the role of TCP. It is a stateful protocol because it keeps track of the state of the communication session. As we already know, the sender receives an acknowledgement that the data was received. TCP tracks which information it has sent and which has been acknowledged. Without acknowledgement, the data is resent. The stateful session begins with session establishment and ends with session termination. In order to gain functions that maintain this state, TCP incurs in additional overhead. As we can see in the picture, each TCP segment has 20 bytes of overhead in the header encapsulating the application layer data. This includes the sequence number with 32 bits used for data reassembly purposes. Acknowledgement number with 32 bits as well indicates the data that has been received. The header length with 4 bits, known as data offset, indicates the length of the TCP segment header. The reserved with 6 bits, reserved for the future. Control bits with 6 bits as well includes bit codes or flags that indicate the purpose and function of the TCP segment. Window size with 16 bits indicates number of segments that can be accepted at one time. Checksum with 16 bits used for error checking of the segment header and data. Urgent 16 bits indicates if data is urgent. Examples of applications that use TCP are web browsers, email, and file transfers. Now it's time for UDP, or User Datagram Protocol. It's a best effort transport protocol, a lightweight transport protocol that offers the same data segmentation and reassembly as TCP, but without reliability and flow control. As we can see in the picture, it has these features. Connectionless. It does not establish a connection between the host before sending data. Unreliable delivery. It does not provide services to ensure that the data will be delivered, as there are no processes to have the sender retransmit lost or corrupted data. No order data reconstruction. If data is received in a different order that it was sent, UDP does not provide any mechanism for reassembling the data in its original sequence. It is delivered as it arrives. No flow control. No mechanisms to control the amount of data transmitted by the source to avoid overwhelming the destination device, because if it is overtaxed, it will most likely drop send data until resources become available. It has no mechanism for automatic retransmission of dropped data. Now let's examine the role of UDP. Although it does not include reliability and flow control mechanisms, UDP's low overhead data delivery makes it an ideal transport protocol for applications that can tolerate some data loss. The pieces of communications in UDP are called datagrams. These datagrams are sent as best effort by the transport layer protocol. Examples of applications that use UDP are DNS, video streaming, and voice over IP. This is because there is a need to deliver live video and voice over the network in a way that data continues to flow quickly. As an opposite to TCP, UDP is a stateless protocol, as it does not keep track of the communication session. It is not concerned with reliability or flow control, as we can see in the picture. Data may be lost or received out of sequence, as it has no recovery or reorder of data.
The key distinction between TPC and UDP is reliability. The reliability of TPC communication is obtained through the use of connection-oriented sessions. Before a host using TCP sends data to another host, TPC initiates a process to create a connection with the destination. The stateful connection enables the tracking of a session or communication stream between the hosts. This process ensures that each host is aware of and prepared for the communication stream. A TPC conversation requires the establishment of a session between the hosts in both directions. After a session has been established and data transfer begins, the destination sends acknowledgments to the source for the segment that it receives. These acknowledgments form the basis of reliability within the TCP sessions. When the source receives acknowledgments, it knows that the data has been successfully delivered and can quit tracking that data. Part of the additional overhead of using TCP is the network traffic generated by acknowledgments and retransmissions. The establishment of sessions creates overhead in the form of additional segments being exchanged. There is also additional overhead on the individual host created by the necessary to keep the track of which segments are awaiting acknowledgments and by the retransmission process. Application process run on servers. A single server may run multiple application processes at the same time. These processes wait until a client initiates communication with a request for information or other services. Each application process running on the server is configured to use a port number, either by the default or manually by a system administrator. An individual server cannot have two services assigned to the same port number within the same transport layer services. A host running a web server application and a file transfer application cannot have both configured to use the same port. When two hosts communicate using TCP, a connection is established before data can be exchanged. After the communication is complete, the sessions are closed and the connection is terminated. The connection and section mechanism enable the TCP's reliability function. Hosts track each data segment within a session and exchange information about what data is received using the information in the TCP header. TCP is a full duplex protocol where each connection represents two one-way communication streams or sessions. To establish the connection, the host performs a three-way handshake. Control bits in the TCP header indicate the process and status of the connection. The three-way handshake are 1. Establishes that the destination device is present on the network. 2. Verifies that the destination device has an active service and is accepting requests on the destination port number that the initializing client intends to use for a session. 3. Informs the destination device that the source client intends to establish a communication session on a port number. In TCP connection, the host client establishes the connection with the server. The three steps in TCP connection establishment are: Step 1. The initializing client requests a client-to-server communication session with the server. In this, a TCP client begins the three-way handshake by sending a segment with the synchronized sequence number SYN, indicating an initial value in the sequence number field in the header. This initial value for the sequence number, known as the initial sequence number ISN, is randomly chosen and is used to begin tracking the flow of data from the client to server for the session. The ISN in the header of each segment is increased by 1 for each byte of data sent from the client to the server as the data conversation continues. Step 2. The server acknowledges the client-to-server communication session and a request a server-to-client communication session. In this, the TCP server must acknowledge the recipient of the SYN segment from the client to establish the session from the client to the server. To do so, the server sends a segment back to the client with the acknowledgement flag set indicates that the acknowledgement number is significant. With this flag set in the segment, the client recognizes this is an acknowledgement that the server receives the SYN from the TCP client. Step 3. The initializing client acknowledges the server-to-client communication session. Finally, the TCP client responds a segment containing an ACK that is response to the TCP SYN sent by the server. There is no user data in this segment. The value in the acknowledgement number field contains one more than ISN received from the server. After both sessions are established between client and servers, all additional segments exchanged in this communication will have the ACK flag set. Security can be added to data network by denying the establishment of TCP sessions, only allowing traffic as part of already established sessions. To close a connection, the finish FYN control flag must be set in the segment header. To end each one-way TCP session, a two-way handshake is used consisting of an FIN segment and an ACK segment. Therefore, to terminate a single conversation supported by TCP, 4 exchanges are needed to end both sessions. 1. When the client has no more data to send in the stream, it sends a segment with the FIN flag set. 2. The server sends an ACK to acknowledge the receipt of the FYN to terminate the session from the client to server. 3. The server sends a FIN to the client to terminate the server to client session. 4. The client responds with an ACK to acknowledge the FIN from the server. When services send data using TCP, segments may arrive at their destination out of order. For the original message to be understood by the recipient, the data in this segment is reassembled into the original order. Sequence numbers are assigned in the header of each packet to achieve this goal. During session setup, initial sequence number ISN is set. This ISN represents the starting value for the bytes from this session that is transmitted to the received application. As data is transmitted during the session, the sequence number is incremented by the numbers of bytes that have been transmitted. This data byte tracking enables each segment to be uniquely identified and acknowledged. One of the functions of TCP is ensuring that each segment reaches its destination. The TCP server on the destination host acknowledges the data that is received by the source application. The sequence number and acknowledgement number are used to confirm receipt of the bytes of data containing the transmitted segment. The HEQ number indicates the relative number of bytes that have been transmitted in this session, including the bytes in the current segment. The TCP uses an ACK number sent back to the source to indicate the next byte that the receiver expects to receive. This is called expectational acknowledgement. TCP also provides mechanisms for flow control. Flow control helps maintaining the reliability of TCP transmission by adjusting the rate of data flow between source and destination for a given session. Flow control is accomplished by limiting the amount of data segments forwarded at one time and by requiring acknowledgement of receipt prior to send more. Another way to control the data flow is to use dynamic window sizes. When network resources are constrained, TCP can reduce the window size to require that the received segments be acknowledged more frequently. This effectively slows down the rate of transmission because the source waits for data to be acknowledged more frequently. UDP is a simple protocol that provides the basic transport layer function. It has much lower overhead than TCP because it's not connection-oriented and does not offer the sophisticated retransmission sequencing and flow control mechanisms to provide reliability. This doesn't mean that the applications that use UDP are always reliable, nor does it mean the UDP is an inferior protocol. It simply means that these functions are not provided by the Transport Layer Protocol and must be implemented elsewhere if required. Although the total number of UDP traffic found on a typical network is often relatively low, key application layer protocols that use UDP include Domain Name System (DNS), Simple Network Management Protocol (SNMP), Dynamic Host Configuration Protocol (DHCP), Routing Information Protocol (RIP), Trivial File Transfer Protocol (TFTP), IP telephony or Voice over IP (VoIP). Some applications, such as online games or VoIP, can tolerate some data loss. If their application uses TCP, they could experience large delays while TCP detects data loss and retransmits data. These delays will be more detrimental to the performance of the application than small data losses. Some applications, such as DNS, simply retry the request if no response is received. Therefore, they do not need TCP to guarantee message delivery. Because UDP is connectionless, sessions are not established before communication takes place, as they are with TCP. UDP is said to be transaction-based, that is, when an application has data to send, it simply sends that data. Many applications that use UDP send small amounts of data that can fit in one more segment. However, some applications send larger amounts of data that must be split into multiple segments. The UDP PDU is referred to as a datagram, although the term segment and datagram are sometimes used interchangeably to describe a transport layer PDU. When multiple datagrams are sent to the destination, they may take different paths and arrive in the wrong order. UDP does not track sequence number the way TCP does. UDP has no way to reorder the datagrams into their transmission order. Therefore, UDP simply resembles the data in order that it was received and forwards it to the application. If the data sequence is important to the application must identify the proper sequence and determine how the data should be processed. After a client has selected the source and destination ports, the same pair of ports is used in the header of all datagrams used in the transaction. For the data returning to the client from the server, the source and the destination port numbers in the datagram header are reserved. Many applications require reliability and other services provided by TCP. These are applications that can tolerate some delay or performance loss due to the overhead imposed by TCP. This makes TCP best suited for applications that need reliable transport and can tolerate some delay. TCP is a great example of how the different layers of the TCP/IP protocol suite have specified roles. Because the Transport Layer Protocol TCP handles all the tasks associated with the segmenting the data stream into segments, reliability, flow control, and reordering of segments, it frees the application from having to manage any of these. The application can simply send the data stream to the transport layer and use the services of TCP. Applications that use TCP include Hypertext Transfer Protocol (HTTP), File Transfer Protocol (FTP), Simple Mail Transfer Protocol (SMTP). There are three types of applications that are best suited for UDP. Applications that can tolerate some data loss but require little or no delay. Applications with simple request and reply transactions. Unidirectional communication where reliability is not required or can be handled by the application. Many video and multimedia applications such as VoIP and Internet Protocol Television (IPTV) use UDP. These applications can tolerate some data loss with a little or no noticeable effect. Some applications handle reliability themselves. These applications do not need the services of TCP and can better use UDP and the Transport Layer Protocol. TFTP is one example of the type of protocol. TFTP has its own mechanism for flow control. error detection, acknowledgements, and error recovery. It does need to rely on TCP for those services. Other types of applications well suited from UDP are those that use simply request and reply transactions. This is where a host sends a request of may or may not receive a reply. One example of this type of application is DCHP. DNS and SNMP are not examples of simple request and reply transactions that most commonly run over UDP. However, these two applications can be run over TCP as well. Thanks for watching.